Now I'd like to talk to you about basically the same thing we just talked about in the other video, except I want to address the same concepts while talking about something called water potential. So water potential allows us to put numbers to this process and apply a little bit of mathematics, and it's an alternative way to explain the events that that we just talked about, like plasmolysis and cytolysis and all that stuff. So let's take a look at this. Now, by the way, the math we're going to do is really easy, but the conceptual idea behind water potential is not so easy, so you want to pay real close attention to that. But the mathematics, we're just basically adding and subtracting. It's pretty simple. All right, it starts kind of scary because water potential has a scary Greek letter called psi, and that's the symbol for water potential. So water potential comes with this formula. It's solute potential and pressure potential. So there's two components to it. Solute potential, so that's the tonicity of the solute drawing the water to it. And then pressure potential is basically the push or the pushing of water away from where the high pressure is. So this thing kind of pulls the water. Oopsie, let's fix that. It pulls the water towards it, like that's what salt would do or sugar. And pressure basically pushes the water away from it. So one of them is going to be positive and one of them is going to be negative. So solute potential is always negative or 0, and pressure potential is always positive or 0. So the highest that any solute potential could ever be is 0, because solutes, like salts and sugar, can never push the water away. They can only pull the water to them. All right, I'll have some more formulas for you in a minute, but let's just do some practice problems using this. All right, let's take a look at, once again, our cup with our cell. And let's say that the pressure out here in this room that we're in is 1 atmosphere, atmospheric pressure. So that's the air pressure in the room from all the air that's above us in the atmosphere. Okay, and that's roughly 1 bar. Now, in chemistry, you might have learned about atmospheres or torr or millimeters of mercury, different units for pressure. In biology, they like to use bar, and 1 bar is almost exactly the same as 1 atmosphere. All right, so we're going to say that the pressure potential out here is 1 bar. I'm just going to write 1, but the unit would be bar, so it's B-A-R. All right. And let's say it's salt water, so the solute potential, now keep in mind, it has to be negative, is going to be -8, let's say. I'm just making up a number. So that's not super concentrated, but it's fairly concentrated salt water. And we can actually calculate what the concentration would be. We'll do that later. All right, inside of the cell we have a certain amount of salt, but not as much. So we have a solute potential of, let's say, -3. I just made that up. It doesn't matter where those numbers came from. That just means it's less salty. The more salty you get, the more negative the number gets. The more negative, the lower the solute potential gets. 0 would be the highest it could ever be. That means no salt at all. Now the pressure inside of an animal cell would also be 1, because the atmospheric pressure, if it wasn't 1, it would change the size of the cell. It would either expand or it would constrict or shrink. So it has to be 1 also. So those two are really going to cancel each other out. And sometimes we write problems where we say the pressure potential is 0. But here I'm just going to try to be realistic. Let's say it's 1. And inside of that animal cell, it'll be the same. All right, so now the inside water potential is going to be the solute potential, which is -3, plus the pressure potential, which is 1. So that's going to be -2. Okay, the outside water potential, I'm sorry, yeah, I'll write it over here, but I don't have space to put it here. It's going to be the solute potential, -8, and plus the pressure potential, which is 1. So that's going to be -7. All right, so in is -2 inside of the cell, outside of the cell is -7. So now we have to take a look at which has a greater water potential. Is the water potential inside of the cell greater or outside of the cell greater? And we might say, well, they're both negative, neither one is greater. Yeah, but -2 is greater than -7, because -7 is a lower number. So this is actually greater, which means the water is going to flow from greater water potential. Oops. Flow is from greater water potential to lower water potential. All right, so since inside of the cell we have greater water potential, water is going to flow out. So that's another way to explain the direction of the water flow without saying concentration of water. We said before the concentration of water was greater inside of the cell. That is true. But we could also say the water potential is greater inside of the cell, and that's going to push the water out. Or you could say the salt is pulling the water out. That's another way to look at it. Either way, the water is going to flow out. And then what's going to happen, I'm going to clean this up a little bit, if I may. Let's see if I can do it quickly. I'm just going to draw what happens then after a certain amount of time. All right, so let's have a certain amount of time expire. Let's say an hour passes or something like that. So what's going to happen is the cell's going to shrink. And so plasmolysis happens. And what's going to happen is eventually the solute potential inside of that cell is going to be the same as the outside. So remember, the outside was -8, so pretty salty. And this started at -3, so way more dilute. But because so much water has diffused out and the salt that was in here stayed, eventually this will also be then -8. Oops, -8, okay. Let me fix that. It's important that we put the negative in. That just still doesn't look very good, but oh well. And then the pressure will still be 1, and the pressure here will be 1. That's the same, because if it wasn't, water would still flow. It would still move. So now the inside, at the end, so let's say before and after. So at the end, the inside water potential is going to be -8 plus 1, which is -7. And the water potential on the outside is going to be -8 plus 1, which is also -7. You might say, well, what about all this water that diffused out? Didn't that dilute this? And shouldn't it be like -7.5? And the answer is the cell is so small that there's negligible amounts of water coming into this beaker, meaning that the concentration out here essentially stayed the same. We couldn't measure the difference. It's like you saying, I'm going to pee in Lake Michigan and then measure how much the salt concentration of Lake Michigan went up. It's not really going to go up just from you peeing in there. Okay, that's gross. Anyway, -7, -7, now they're the same, so there's no more net flow. Flowing out and flowing in is now equal. No more net movement of water, and we're at equilibrium. The two solutions are isotonic. Sorry about the squeaking chair. All right, so we got that. What about hypotonic solution? Yeah, let's try that once. All right, let's throw a cell in a hypotonic solution. Here's our cell. And if it's hypotonic, you'll have to know that that solute potential in there is, I could probably write it in there. I got enough space. So the solute potential of this is as high as it possibly could be. That means there's no salt at all, so it's 0, because it's pure water. Hypotonic, okay? Hypotonic. All right. Pressure, we'll say, is 1. We'll keep that the same to make it easy. Pressure inside of animal cell is 1 because if it's an animal cell, it's flimsy, and it's going to be equal to the other one. All right, and in here we said it was -3, which is about what, that's actually about what cells are. That's kind of realistic. Oh, that cursor is annoying. Let's get rid of that. Okay, so now we have to look at, okay, let's do inside. Water potential on the inside is solute potential, -3, plus pressure potential, 1, that's -2. Water potential on the outside is going to be solute potential, 0, plus 1, pressure potential is 1. 1 is greater than -2. That means out here the water potential is greater, and water is going to flow from greater water potential to lower water potential, which is -2. So it's going to flow in. Water flows in, the cell swells, and eventually this happens. And we already know the answer. It's going to burst. I'm going to burst. And after it's bursted and you wait long enough and everything's been sort of equalized, what you're going to have is a solute potential inside of the cell, because there's really no more inside of the cell because it burst, of 0. Well, what about all these solutes you spelled? It's so small that's not going to make a difference. Pressure is 1, because that's still atmospheric pressure. Out here, solute potential is 0, and pressure potential is 1. So now our water potential inside is 1, and our water potential outside is 1. If you want to still consider this the inside of the cell because it burst open, there really is no more closed off inside of the cell. Everything is basically the same at this point. And once again, that's called plasmolysis, as you already know. Okie dokie. In the next video, we'll talk about plant cells.